Great to see everyone. I'm Justin, and thanks you for coming to the talk here. Super cool event, by the way. This is my first Progress conference. I guess it's most people's first, even though because it's the second ever. But anyways, super excited to talk about the grid today, and sort of give you the perspective as we have at my company and what I have, which is it's really the most critical link to unlocking progress in energy, maybe even more so than generation and other topics around the energy revolution. So just as a really quick background on myself before we dive in, I started at SpaceX. My career was down in Brownsville, Texas. We were building the Starship facility and led manufacturing for the company down there at Starbase. Then more recently was at a company called Anduril. Most folks are familiar with that, does defense technology. Was leading manufacturing operations for them. And then now started a company called Base Power. We're based in Austin, Texas. I'll tell you a little bit more about what we do. That is looking to solve the challenge of the grid and what we're going to discuss today. So the talk is going to be somewhat technical and detailed around the grid. So happy to have folks just like ask questions along the way. We're talking about what is the grid and some of its history, where we're at now, and our proposal on how we set ourselves up for success, as well as how the reindustrialization movement really enables a lot of what we're doing on the grid, and I think is part of the bottleneck to adding capacity to the grid. So I'd love to start with what is the grid. The way to think about it is it connects supply and demand. It connects generators and load, sellers and buyers. This is a helpful like graphic on the left as to the sort of physical layer of the grid. The way I like to think about it actually is the grid has sort of two layers. There's the physical layer, the one that you see and can touch. You shouldn't generally touch, but you can physically touch if you wanted to. And then there's like the financial and markets layer, which is equally important and is shown on the right, and I'll get into that in a second. So on the physical layer, you have like the very traditional model of the grid is a one-way street. And I'm going to explain later why I think that the grid really should be a network and a two-way street, but the traditional model is a one-way street where the power plant outside of the town generates electricity. It's stepped up for transmission. Transmission is the like tall poles with wires. It goes down to a substation, which it gets transformed down to a lower voltage. And then it goes to what's called distribution, which are typically, but not always, wood poles at lower elevation. And then it goes to your home, transformed down to 120 or 240 volts. So this is like the grid. The grid contains generation, transmission and distribution, and retail sales to either a home or a business. You can see down here in the U.S. roughly the total length of all of the wires in transmission and distribution. You can see there's almost a 10x difference in distribution versus transmission, and we'll get into why that's important later. But the point is, there's a lot of miles of wire that makes up the grid. The grid is the largest physical asset in the world. On the right side of this screen here is map of the U.S., obviously, and it shows a few different layers stacked up here. So again, remember the physical layer versus the financial layer. So the physical layer is shown here also. There are three interconnections or three grids in the U.S. You have the western interconnection, which is kind of this half to the left of this white line. You have the eastern half, kind of east of Colorado and the Rockies here, and then you have Texas. And there are three interconnections, meaning like, an electron could flow from Detroit to Minneapolis to Miami, but it can't flow to Houston, and it can't flow to where we are in San Francisco. An electron could flow from San Francisco, actually could go to El Paso technically, but it couldn't go to Brownsville, where I was previously, but it could go to, Oregon as an example. So that's the physical layer. Now the financial layer is what's in the shaded colors here. So there are regions that are called RTO regions, regional transmission operator regions, and then there are non-RTO regions. And each one of these RTO regions that's denoted by the dotted line here shows a different financial market for that region. So you can see like most but not all of California is shaded in blue here. There's a financial market where the sellers of electricity, the generators, and the buyers of electricity can trade electricity with each other through that marketplace. That marketplace is called CAISO, the California Independent System Operator. There's one in Texas called ERCOT, the Electric Reliability Council of Texas. Those are just names. The point is that there's a financial layer that sits on top of the physical layer, and those two things don't necessarily match in terms of their geography. So that's the grid. So let's talk a little bit more about the market participants. Again, thinking about the both physical and financial layer. So you've got the generators. Pick your favorite generation source. They make the power. You've got like the actual grid itself, transmission distribution, oftentimes referred to as just utilities. And utilities transmit and distribute the power. And then you've got the power companies or the retailers. And so in a place like California, specifically up here in Northern California, PG&E is the utility, and they're what's called a vertically integrated utility, meaning they do all three. They sell you power. In fact, you have to buy power from them if you're in this area. They own the poles and wires. Like if you drive around and you look at some logos on the poles and wires, you'll oftentimes see a PG&E logo. And they own generation. So they have nuclear and coal and wind and I think solar plants as well. Now, this is not always the case. Like a place like Texas, these three things are different. In fact, most of Texas is what's considered deregulated, meaning the infrastructure operator, the utility, can't sell you power and they can't generate the power. They can only transmit the power. And then you have IPPs, independent power producers, that own generation, but they can't sell retail, or at least some do, some don't. So again, three different market participants in different areas of the grid. So you're probably like, wow, this is a weird way to build a market and a physical infrastructure. You'd be right. It's really complicated, and it's also very different from state to state. And one of the things we're going to talk about later is that's a problem for increasing capacity and adding more infrastructure to support the new loads that are coming on the grid. If we zoom into just what's in green here, the infrastructure operators piece, there are now three different types of utilities, and I promise the complexity will stop at some point. So there's investor-owned utilities, which is roughly 70% of utilities, and it's what it sounds like. Like PG&E, you can buy stock in, as an example. It's just a company, and the way that they make money is by what's called ROE, return on equity. So they go put $1 into capital expenditures, like standing up a new wire to a new home community, and then they earn $1.09 typically. It's like typically a 9% rate of return. It's a cost-plus business model. The reason this is important is because it's different between the other two. So there are government-owned utilities, like LADWP down in SoCal, and that is literally just the government owns the utility. They don't have a return on equity because there is no concept there because it's part of the government. And so really they just try to lower costs for consumers. They're not super efficient at doing it all the time, but that's their sort of goal in life, is like deliver the electricity as cheaply as reasonably possible. Then there's an interesting concept called cooperatives. And if you look, this map, all of the shaded area is cooperatives. It's like most of the land area in the US is actually served by a nonprofit cooperative. And it's a nonprofit corporation that's like basically born out of a rural commune. It was like one farmer with a windmill and one farmer with a grain mill, and they connected the windmill to the grain mill, and then they started building this cooperative. And they actually are typically the most efficient out of the three. It's kind of weird, but they own the poles and wires. They oftentimes own generation, and they have a monopoly on selling electricity. And you can see that Californians, you're probably like, what's a cooperative? Because most of California doesn't have cooperatives, but most of the rest of the U.S. does have a bunch of cooperatives. There's actually several hundred cooperatives throughout the U.S. Okay, so that's like, what is the grid? Who owns it? Who operates it? Who are the players in the market? Now, where are we at? So I put this slide together that shows two main things that are really tying to the same point, which is utilization. So if you think about a wire running through the grid somewhere, utilization is basically like how much of the time is it used for what percentage of its capacity. So on the left, this is utilization in the industry term, a load factor by the utility area. So for instance, you can see ERCOT here. ERCOT's Texas, and in aggregate between the winter and the summer, 53% of the capacity of the grid is being used. And you're like, okay, well then what's the problem? You just got 47% more to go. The answer is that sometimes it gets to 100%. And in some months, in particular in ERCOT in the summer, because it gets hot in Texas, you're actually using a lot more of it. The challenge is not like any day on the grid. The challenge is the one day, which is the hottest or the coldest of the year, because that's what the entire system has to be built to. It has to be built to the peak load. This goes to show that like even in the best case, this is the mid-continent, you're at like 60% utilization. That's pretty low for the most expensive and largest capital asset in the world. And then on the right, this is a similar view of what's on the left, but this basically says what percentage of the hours are you at maximum percentage of the system peak? And what this goes to show is like 1 or 0.5% of the hours are you at 90%, but most of the time you're at a really low percentage of utilization. Again, utilization really, really matters because an underutilized, very expensive capital asset means that everybody is paying more for the thing to work in that 1 or 2 hours a year. So again, the whole system is sized for peak. And so what has that resulted in? That's resulted in the cost of delivering bottom bars here going up, whereas actually the cost of producing that electricity is going down. And so this is the fundamental challenge that the grid has to solve, is how do you get the top of the bar to go down? Between 2010 and 2020, this is EIA data, the top of the bar basically didn't move. Power prices roughly stayed the same, and like if you're on Twitter, you see the fast rising electricity costs. If you extended this out, it actually has gotten worse. Power delivery has gone up a ton. Power production has continued to go down, largely because of the advances in modern nuclear, solar, and wind primarily. And so, what do we do about it? One last point here on how we're investing in the grid. So you're like, maybe we should invest more into the dark blue bar and build more capacity. We haven't been doing that. Well, we've been investing more, but we haven't been actually for it. So this is miles of transmission lines built per year, clear downtrend, obviously. And then this is in each area that's shaded here in the U.S. map, how much distribution and transmission investment has gone in. You can see we are building less and spending more. And the cost of, again, this is reinforcing the prior slide or two prior slides, but the cost of generating electricity has roughly remained the same for our two largest sources, which are coal and gas. Solar has come down a massive amount, so has wind, and so have natural gas. Okay, so one of the solutions that has been built to manage this utilization issue is what's called grid scale storage. So think like a shipping container or a bunch of shipping containers in the middle of the grid, so to speak, connected typically into transmission. This is my pretty bad drawing of that. So this is great because when generation is intermittent, if you have a bunch of solar, you can like store a bunch of excess in the battery and then you discharge it at night. And now the solar farm looks like a natural gas plant from the grid's perspective. And that's fine. It just doesn't solve the utilization problem that I was talking about earlier. It only really just solves intermittency of generation. Now I'm going to talk to you about what I believe is the future of the grid, which is adding storage, but doing it at the edge, at the consumption end. This is one, I should say, not the only future, but part of the future of the grid. Isaiah just presented on future of the grid on the generation side. That is important and matters, and we will need a lot more of that. What I'm here to talk about today, though, is really on adding storage at the edge of the grid, co-located with consumption. The reason why I and my company believe this is the solution for increasing the amount of electricity that we can deliver is a fewfold. One is that it increases utilization. So imagine it's August 15th in Houston. It's 115 degrees out and 100% humidity. Everybody's running their air conditioning, and you have a neighborhood with a bunch of batteries on it. You can now turn off that home or those homes from the grid during those peak times and serve them with the battery. So now that grid does not have to handle that additional load, and it has increased its utilization. This is what my company, Base Power, does. We put batteries on homes, we aggregate them through our software, and we bid them into the wholesale markets, primarily in Texas, and we offset the peak loads during peak times, and we increase the trough loads during the overnight times typically, and that increases utilization. And so now you can add more load onto the grid, you can hook up more data centers, you can put more EVs on the grid, you can build more manufacturing facilities here in the US, but you don't have to build more grid every time you put more load on it. There are other things on the sort of regulatory side that enable what we're doing, and I think ultimately lead to a more efficiently utilized grid. There's three things that I've called out here. One is permitting. I don't need to belabor the point here. Everybody knows permitting sort of sucks, basically, represented by my favorite movie ever, Zootopia. And you can see that like permitting is a big problem. Again, I don't have to go into a ton of detail there, but building new infrastructure, whether it's batteries on homes or more transmission lines or nuclear plants, et cetera, permitting is an issue. The other is actually a little bit counterintuitive for someone that is like very much for, adding adding batteries to the grid that oftentimes are subsidized by the federal government, but actually is removal of subsidies. There's a distortion in the market today for a lot of different energy technologies, solar, wind, batteries, etc., and removing those, some of which is already taking place, actually, I believe, will enable the free market to really put forth the best and most effective solutions. And then I think the real root cause of a lot of the challenges that we have in terms of the efficient utilization of, again, the largest capital asset in the world is utility incentives. So as I mentioned many slides ago, most utilities are investor-owned, and those investor-owned utilities have a cost-plus business model. They earn a rate of return for every dollar they put into the grid. And this is a map of all of the investor-owned utilities. You can see PG&E up here covers most of Northern California, SoCal Edison down in Southern California. They have no incentive. The utilities have no incentive to innovate, to attract top talent, to utilize their system more efficiently. Their incentive is to spend money. And that is what is driving costs up, as I mentioned on prior slides. And the last point I want to make before we wrap here and have time for some questions and discussion is reindustrialization. This word gets thrown around a lot, and I think wanted to highlight a few areas where the U.S. is lacking capacity in comparison to China and other nations as it relates to adding capacity to the grid. So number one is transformers. Some folks may have heard of this challenge. Transformers are in a big shortage for U.S. utilities, and all the way back, I won't zoom all the way back, but if you looked at the map of the physical infrastructure of the grid, you can see there are transformers at basically every step. This is a big blocker for many utilities, and there are some startups and companies that are working on this, but there are long lead times and very high costs for transformers, a lot of which is driven by supply chains within the transformer ecosystem themselves. This is something that we deal with a lot, are battery cells. So about a third of the market is taken up by two companies, which is CATL and BYD, both Chinese companies. And you can see that like most of the other companies for LFP production are in China. You can see some are in the US and in East Asia. But there's very little battery cell production for grid scale applications here in the US, something that we are very passionate about working on. And the last thing, this is now, even since I made these slides, now more relevant than it was before, but raw material, critical mineral mining and refining is also something that we need to bring back to the US, not even just the rare earths, but copper as an example and aluminum for all of our conductors and other materials that go into batteries as well. And so even if we were to go put distributed batteries everywhere, that would be pretty hard because we need a lot more of this stuff. And so there's a number of companies and a lot of effort now fueled by the American Dynamism folks and others that are putting capital into solutions that solve these problems. And the last thing here is on the reindustrialization front is upskilling. All of the infrastructure that I just talked about for the last 20 or 25 minutes needs to be built and physically installed and constructed by people. Unfortunately, this is an area that is very hard to automate. It's hard to automate putting poles and wires up. It just is. Same thing for transformers. It's really a construction-intensive industry. Manufacturing of batteries, of course, can be automated. Manufacturing of transformers can be, but the actual laying of the poles and wires is hard to do without humans. And there's a critical shortage of electricians and linemen and others in the country. I'd like to think we're doing our small part as a company on the electrician side in particular by upskilling and working with local trade schools. But there's a large need for this as well, and something that I'm particularly personally passionate about, and I think a lot of folks in the room, I imagine, are as well. Partially, labor costs have increased, and so because of the high labor content, the cost of installation of poles and wires basically has gone up. The other, and a large portion of the other, and if you look at, and I don't have a great graphic on this, there's some also EIA data out, but if you look at the total cost of building out infrastructure, a lot of it is on the left here. Like there's a lot of permitting, environmental review, and overhead costs that are built in, and those costs are going up. Okay, cool. Thanks.